In this video, we'll be going over exponential and logarithmic functions. So let's first look at exponential functions. An exponential function is a function of the form f of x equals to a to the x, where x is our variable, a is the constant and it's called the base of the function, but a must be greater than 0 and it cannot be 1. And domain of the function is going to be negative infinity to positive infinity, which is all real numbers. So when we look at a graph of an exponential function, on the left here is a graph of f of x equals to a to the x if a is greater than 1. So coming from the left, it moves up to infinity to the right. So some notable things to consider on this exponential function is that exponential functions always have to have a horizontal asymptote. So the parent function of an exponential function has a horizontal asymptote at y equals 0, and it also has a y-intercept at 0, 1. So it crosses the y-axis at 0, 1. Now, the graph on the right depicts an exponential function if our a is between 0 and 1. So it can be in a fractional form like 1/2 or 1/3. So now, coming from the left, it actually goes down towards 0. So it dips down to the right. It's actually a mirror across the y-axis from the graph to the left. But the same components apply. It still has a horizontal asymptote at y equals 0, and it still has a y-intercept at 0, 1. So an example of an exponential graph is we have the graph of f of x equals to 1/2 to the power of x. So notice that our a value here, this is our a value, and it is less than 1, but it's greater than 0. Therefore, the graph, instead of coming from the left and going up, it's coming from the left, but it's going downward. So it's moving down towards 0 here. But it still has a y-intercept right here at 0, 1, and it still has a horizontal asymptote at y equals 0. Now, when talking about transformations of exponential functions, here are some steps on how to find them. So first what I do is identify the parent function and then graph it. So the parent function is going to have the form of f of x equals to a to the x, where again a has to be greater than 0 and a cannot be 1. And then we will apply the transformations to the parent function following the order of operations. So very similar to other types of functions, we have similar process. So reflections across either the y-axis or the x-axis are as follows: y equals to negative a to the x, or y equals to a to the negative x. So the first one here, y equals to negative a to the x, is our horizontal reflection. So it reflects across the x-axis, while a to the negative x reflects across the y-axis. So number 2 is stretches and compressions. So when you have y equals to k to the x, or y equals to a to the power of kx, that's our different type of stretches or compression. So when the k is on the outside, as opposed to this first one here, it's considered a vertical compression or stretch. And then when it's a to the power of kx, the k would be a horizontal or horizontal stretch or compression. Now, number 3 is a horizontal shift. So if you have y equals to a to the power of x plus or minus k, that would shift it left or right. And number 4, we have vertical shifts, is when you have y equals to a to the x plus or minus k. So when it's on the outside of the function, it would move it up or down, respectively. One thing to consider, though, for the horizontal shift is that if it says x minus k, it's actually moving to the right. If it's saying x plus k, it's moving to the left. So let's see this being implemented in an example. So the example says, graph the following functions. We have f of x equals to 3 to the x plus 1 minus 2. So the first thing we want to identify is our base. The base here would be 3, so that's our A, and we know that A is greater than 1, so it's coming from the left and it goes up. Now, what is our transformations? So we see there's that +1 on the inside the power and that -2 on the side. So the +1 in the power, because it's essentially on the inside, we can consider it a horizontal shift. So we'd say it's a horizontal shift. And because it's a +1, you think opposite, so we're actually shifting it left 1. Now, the -2 is on the outside of our function, so that would actually be a vertical shift. And that would just be, because it's a -2, it would be down 2. So if we were to draw the parent function of this, f of x equals to 3 to the x without any transformations, what it would look like is it would be like this, coming from here and cutting through this middle part and going upward. Now the reason why it's cutting in between here specifically is because our graph is actually, each tick mark is going by 2. So this point right here is 0, 1. So we would call this 3 to the x. So comparing this blue line with our red is the given function, 3 to the x plus 1 minus 2. We notice that's being shifted down 2 units and being shifted to the left 1. So that would be our graph. So another example, we have f of x equals to -1/4 raised to the x plus 3. So first things first is we need to find out what our base is, our a. Our a in this case would be 1/4, which is less than 1, so it'd actually be coming from the right and dipping down. So think about our transformations. So we have a negative in front and then a +3 at the end. So the negative in front would actually be a reflection, and it would be reflection across the x-axis, to be exact. Reflection of x-axis. And then the +3, just like before, is a vertical shift of up 3. So if we think about the parent function, let's call it h of x, is 1/4 to the x power. So it'll be coming from the right here and going up like so. And again, this point right here is going to be 0, 1, where across the y-axis. So as we said before, what's happening for us is that not only is it shifting up 3 units, it's actually being flipped across the x-axis. So that's what our function, -1/4 x plus 3, that's what it will look like in the red right here. Now we move on to solving exponential functions. So in order to solve an exponential function, we can compare both sides. So what that means is that in order for them to be solved, the left side and the right side, they need to have the same base. So if we have a to the m equals to a to the n, then m equals to n. So if we take that logic, let's solve an example here. So we have 27 to the x equals to 3. So we look at the bases on both sides here. We have a 27 on the left and a 3 on the right. Obviously, they're not the same. So we need to somehow make them into the same base. Now, if you notice, 27 is actually can be written with a base 3, because we can say this is 3 to the third equals to 27. So therefore, we can replace the left-hand side here, 27 to the x, with 3 to the third raised to the x equals to 3. Now, when you raise a power to the power on the left side, according to exponent rules, we would just multiply. So we have 3 to the 3x equals to 3. And then think about 3 can actually be written as 3 to the 1. So now we've written the left-hand side and the right-hand side in exponential form. And because our bases are the same, we can now set the powers equal to each other. So we can set 3x equals to 1, which allows us to solve for x. We can divide both sides by 3. So x has to be 1/3. And that would make our equation true. All right, so let's look at couple more examples. Number 2 here, we have 64 to the p equals to 8 to the p plus 2. So the first thing we need to do is we need to convert both of these exponentials into the same base. So you know 64 can actually be rewritten as 8 to the power of 2. So what we do is we would substitute on the left side 64 and write it as 8 to the power of 2, which is still being raised to the p, and that's equal to 8 to the p plus 2. Now, using the rules for exponents, we know that 8 to the power of 2 raised to the power of p is, we're just multiplying them, gives us 8 to the 2p equals to 8 to the p plus 2. Now that our bases are the same, we can set both of our exponents, our powers, equal to each other and solve for p. So we can subtract p both sides, gives us just p equals to 2. And that is our solution. Now moving on to number 3, we have 1/3 raised to the x plus 2, and we have equals to 3 to the x minus 1. So when we look at 1/3, we can actually, again, use the rules for exponents. As a reminder, if you have 1 over x to the n, that can be written as x to the negative n power. So we apply that to our left-hand side of our equation. So 1/3 can be written as 3 to the power of negative 1 raised to the x plus 2 equals to 3 to the x minus 1. Again, apply our rules for exponents when raising a power to power. We distribute this negative 1 to the x plus 2. So we would have 3 to the negative x minus 2 equals to 3 to the x minus 1. So now our bases are the same. They both have a base of 3. We can now equate the powers. So we can write this as negative x minus 2 equals to x minus 1. So let's solve for x. We can subtract x both sides and move it to the left. So we have negative 2x minus 2 equals negative 1. And then we would add this 2, gives us negative 2x equals to 1. And the last step is divide both sides by negative 2. So x equals to negative 1/2. And that would be our solution to number 3. Now let's look at logarithmic functions. A logarithmic function is a function of the form y equals to log base a of x, where a is a constant called the base of the logarithm, a is greater than 0, and a cannot be 1, and x is our positive real number. And the domain of a log is going to be all real numbers greater than 0. So it goes from 0 to infinity. Now notice, comparing this to our exponential functions, they have very similar components. They have a base a and a variable x. So we can say that the logarithmic function with base a is actually inverse of the exponential function in base a. So we have y equals to log base a of x. It's equivalent to writing as x equals to a to the y. So we will see in a minute why this makes sense graphically. So let's look at the graph of a logarithmic function. So on the left here, we have f of x equals to log base a of x if a is greater than 1. So this time, instead of it having a y-intercept, it actually has an x-intercept at 1, 0. And also, it has, instead of having a horizontal asymptote, it now has a vertical asymptote at x equals 0. And instead of coming from the left and going up, it's actually coming from the bottom and going up to the right. So it's moving along here and going over to the right side. Now, the graph on the right is the same, f of x equals log base a of x, but this time our a is between 0 and 1. So this time it's coming from above and it's going down to the right, but it still has a vertical asymptote at x equals 0 and an x-intercept of 1, 0. Now, notice how these two graphs are actually inverses of the exponential graphs that we discussed earlier. So when we look at the graph of f of x equals log base 2, it still has a base of 2, so that means a is greater than 1, so it's going to come from the bottom and move to the right, but it still will have a vertical asymptote at x equals 0 and an x-intercept at 1, 0. Now let's look at transformations of log functions. So first thing we're going to do is we want to identify the parent function and graph it. So the parent function is going to have the form of f of x equals to log base a of x, where a is greater than 0 and a cannot be 1. So then we apply, just like for exponential functions, we apply the transformations to the parent functions as follows. So number 1, reflections. So if you have y equals to log base a of x, or y equals to log base a of negative x, that's a reflection. So just like before, this would be a horizontal reflection, so reflection across the x-axis for when it's on the outside. And if the negative is on the inside, it will reflect across the y-axis. Number 2, stretches or compressions. Y equals to k times log base a of x, or y equals to log base a of k times x. So again, if the k is on the outside, it's actually a vertical stretch. And if it's on the inside, it's a horizontal. So now, number 3, horizontal shift, is if it's in the form of y equals to log base a of x plus or minus h. Now, the key thing here is that, just like before, if it's a plus, it's actually moving to the left. If it's on the right, if it's a negative, it's moving to the right. And lastly, we have vertical shifts. So y equals to log base a of x plus or minus k. So we take this at face value. So if it's a plus, we move up. If it's a minus, we move down. So these transformations apply to not only exponentials, but the same rules apply to other types of functions as well. Okay, so let's look at these transformations in an example. So we have f of x equals to log base 1/2 of x plus 3 minus 1. So first thing we do is we want to identify what our base is. So our base here, a, is going to be 1/2. So it's going to come from the top and move down to the right. We have a plus 3 and a minus 1. So the plus 3 is going to be a horizontal shift. And because it's a plus 3, it actually shifts it to the left 3. And then we have a minus 1 that on the outside, and that would be a vertical shift. And that would be taken at face value, that would just be down 1. So as shown to our graph here, our graph is being moved to the left 3 units, and it's going to be moving down 1. So another example, we have f of x equals to negative log base 3 of x minus 1 plus 2. First thing we need to do is identify what is the base of our log. The base of the log would be 3. A is equal to 3, which means that it's going to come from the bottom and move up to the right. However, let's look at our transformations here. We have a negative in front of the log. We have a negative 1 on the inside of the log. And we have a plus 2 on the outside of our log. So that negative in front of a log would actually be a reflection across the x-axis. The minus 1 on the inside of our log would be a horizontal shift, but it would be a horizontal shift, and you think opposite, so it'll be right 1. And then finally, the plus 2 would be a vertical shift. And because it's just a plus 2, it would just be up 2. So if we think about our parent function, let's say we call it g of x, that would be just log base 3 of x. So it's coming from the bottom here, and it's cutting it. It's going to hit the x-axis right here in the middle. And the reason why it's on the middle is because it's not at, this point here is 0, 1, but because of the scaling of our graph, each tick mark is actually going by 2. So we'll be hitting right in the middle. That's considered 1. And I apologize, that would actually be 1, 0, not 0, 1. So this point here would be 1, 0. So comparing that blue line is our g of x is log base 3 of x. So comparing it to the red line, which is the actual f of x function, we see that it's being flipped across the x-axis, it's being shifted to right 1, and it's being moved up 2 units. And that will be the graph of f of x. Another thing to consider when it comes to logarithmic functions are its different properties that we need to know. So the main properties we need to focus on are the product property, the quotient property, the power property, and the change of base property. So power property basically says when you have log base a of m times n, you can write it as 2 log functions of log base a of m plus log base a of n. The same thing can be said for the quotient property. When you have log of m divided by n, you can turn that into log of m minus log of n. The power property says if you have log of m to the r power, you're allowed to move the r down to the front of the log function, or vice versa. So you can move the r up and down as you need it. Now, the change of base formula is when you have of log base a of m, you can actually rewrite this as log base b of m divided by log base b of a. And the reason why that needs to be done is if you don't have access to a calculator, because calculators by default only have log of base 10 or a natural log. So if you're given a situation where we have log base 3 of 5 and you can't calculate that, so what you would do is you would say your base is a, and this is our m. So then you can rewrite this as some known log function, either a natural log or log of base 10. You can write it as ln of 5 over ln of 3, or log 5 divided by log 3 in order to calculate it. And then the last thing we want to talk about is the inverse property that can be used to, as we talked about earlier, is logs and exponentials are equivalent to each other. So you can write a function in either log form or exponential form. And if you want to get rid of either an exponent, the exponential, or a logarithm, you would apply the inverse of it. Okay, let's use our properties that we just learned to rewrite this expression. So we have log base 4 of the square root of 4x to the 5th divided by z times y to the 7th. So the first thing we notice is that we have a square root around everything. So remember, square roots can actually be written in exponent form. You can actually write it as a power of 1/2. So let's do that. So let's rewrite this log base 4 of 4x to the 5th divided by zy to the 7th, all raised to the 1/2 power. So then now we can actually apply, the first property we'll apply is the power property, because we can move this 1/2 power to the very front. The reason why we do that one first is because in order to split our logs, the power should always have a power of 1. We don't want any other power there. So we want to keep that power as a power of 1 before we even start splitting it. So now we look at what we have on the inside here. We have 4x to the 5th divided by z times y to the 7th. So that division is a quotient. So we can apply the quotient property. So the quotient property states if we have something divided by something, we can split it as log of the top minus log of the bottom. So you want to still keep in mind though that that 1/2 should still be in the front. So we can write this as 1/2 bracket log base 4, make sure I have the 4 here, of 4x to the 5th minus log base 4 of z times y to the 7th. So then now we can go even further because each of these logs here, it's 4x times 4x to the 5th. That's like saying 4 times x to the 5th. And the other log has z times y to the 7th. So multiplication is a product. So that's going to be applying the product property. So we can now rewrite this as 1/2 bracket log base 4 of the first term, so that's 4, plus log base 4 of x to the 5th minus, so let's do some parentheses because minus all of this log here. So log base 4 of z plus log base 4 of y to the 7th and close bracket. So we want to check, can we do any further with this? We can, because there's some things here, because we can actually apply the inverse property to this one here, because when you have the base of the log and the base of your exponent are the same, they essentially can cancel each other out, and you're left with just whatever the exponent is, which it would be 1 in this case. So we would have a 1 here, and in anything that has an exponent, we still apply the power property, so we need to bring the power down. So when we have log base 4 of x to the 5th, that can be written as 5 log base 4 of x, and then apply this negative here, so it'd be negative log base 4 of z. And then this y to the 7th here, we can bring the 7 down to the front, it'd be minus 7 log base 4 of y. So we see that we've split everything else. There's no division going on, there's no multiplication going on, and there's no more powers. So we should be finished, and the last thing we could do is just multiply everything in the bracket by 1/2. So that will give us 1/2 plus 5/2 log base 4 of x minus 1/2 log base 4 of z minus 7/2 log base 4 of y. And that would how we would expand the following expression. So we expanded our logs. Now let's think about actually condensing into one single log. So use the properties of the logarithms to write each expression as a single logarithm with a coefficient of 1. So when we look at this, we have 1/4 log base 2 of 16x to the 4th minus log base 2 3y to the 4th. So the first thing we can do is we see that the first log here has a 1/4 in the coefficient. But because we want our logarithms to have just a coefficient of 1, we have to apply the power property and move that 1/4 back up. So we're shifting it back up. So it's going to look like log base 2 of 16x to the 4th, and we're going to put parentheses around this and raise that 1/4 up to a power. And let's rewrite the other log, so minus log base 2 3y to the 4th power. Now, when we look at that first log, we see it's 16x to the 4th being raised to the 1/4 power. So we can actually apply that 1/4 power to the 16x 4th. Because if you apply 16 and raise it to a 4th power, that's like taking a 4th root of 16, which would actually be 2. So it'd be log base 2 of 2, and then x to the 4th raised to the 4th power just becomes x to the 4/4, which is just going to be x, minus log base 2 of 3y to the 4th. So from there, we can now do a couple things, because we can say that we have log base 2 of 2x minus log base 2 of 3 divided to the fourth. So we notice there's a minus between the two logs. For the properties of logs, when we see a minus, we can always associate that with the quotient rule. So we can say this can be rewritten as a singular log base 2 of the first one, so 2x, divided by the second term, 3y to the fourth. So now we double check. Is this a single log? It is. Does it have a coefficient of 1? And yes, it does. So this is how we would condense these two logs into a singular log. And lastly, let's look at an example where we use the change of base property to approximate a log to 4 decimal places. So we have log base 7 of 25. So if you had a calculator where you're not able to actually fill in the base of a log, on most calculators, standard is you have a button for log and you have a button for ln. Log, by default, when you see just log, it's log base 10. And natural log, ln, is actually log base e. So we need to figure out what log base 7 of 25 is by using the change of base formula. So what we can do is we know that this is going to be our base a, and this is our m. So using the change of base property, we can actually rewrite this as log of the m divided by log of our base, or we can use ln as well. ln of 25 divided by ln of 7. So either method should give us the correct answer. So if we use a calculator now, we can actually get that right answer. So if we take log of 25 divided by log of 7, that should give us 1.6541, but we round to 4 decimal places, so we actually round up 6542. So either use log 25 divided by log 7 or ln 25 divided by ln 7. It will get you the same result using the change of base formula.